Today I'd like to talk about a lot of the different dynamics that are going on in the greater Yellowstone ecosystem. It's a really difficult ecosystem to manage. And when we talk about ecosystems and the definition of an ecosystem, a lot of times it's described as self-sustaining, but there are many dynamics within ecosystems, and ecosystems literally can transition from one type of an ecosystem to another over time. And so that's really what I want to look at first. So this transition from one ecosystem to another over time is known as succession. And there are two types of succession that we see in nature and actually ongoing in the Yellowstone ecosystem. And the first of these is primary succession. So, and the other is secondary succession, which we'll get to in a couple of minutes. So in succession, regardless of which type we're talking about, there are transitions. And early in succession, we see what are known as pioneer species. And these pioneer species typically are annuals, although in the case of primary succession, that's actually lichens, but things that are fairly short-lived. And then over time, they transition into longer-lived plants, which would be equilibrium species. These help contribute and hold the soil. And then as soil accumulates, again, we get more species diversity. And eventually, some particular species will dominate, and this is what's known as the climax species. And so typically, ecosystems, terrestrial ecosystems, then are named for these climax species. So a number of factors contribute to the makeup of an ecosystem. So we have the physical factors such as climate, geology, geography, latitude, altitude would be part of this as well. And then that determines the producers. Producers in turn determine the consumers. But there is feedback. So consumers can have some influence on the type of producers in an ecosystem. Producers can physically alter the environment as well. So it's not just a one-way flow. So this is part of what's at work in succession. So in primary succession is succession that begins on bare rock or someplace where there has been no previous vegetation. And so there's a lot of granitic formations throughout the Yellowstone ecosystem, and so this would be a place where primary succession begins. And in primary succession, typically the pioneer species would include lichens. And we've talked about lichens before, composed of both fungi and algae. And the fungi will produce acids that can break down the rock over time. This contributes to soil formation. And as soil accumulates then, this gives grasses and other annuals, which would be plants that live for a year at a time, a chance to get going. So again, we've talked about lichens before. Typically on rocks, you'll get these crustose lichens growing. Then grasses and other annuals will grow, sometimes some biannuals, some plants that can live for a couple of years at a time. And so they help hold soil, and as they grow, die, and decompose, they contribute to soil formation as well. So these would constitute the pioneer species in primary succession. Then over time, these are replaced by, and fireweed would also be an example of a plant in the Yellowstone ecosystem that would be a real common example here. And then over time, these are replaced by different types of shrubs. And so a lot of the berries that we see in the ecosystem, buffalo berry, western serviceberry, wild raspberry, thimbleberry, all of these would be some of the types of plants then that succeed the grasses and annuals and fireweeds as soil accumulates. And they tend to live a little bit longer. Then also trees can get started, and so you'll end up with mixed forests, mixed conifers in this case. Sometimes you'll have some broadleaf aspens mixed in there as well. And then eventually, one species will typically dominate depending on the makeup of the soil and where it is. And so this mixed forest then will transition eventually into a mature climax forest. But again, the shrubs and mixed forest constitute the equilibrium species. And then again, the climax species will be whatever ends up dominating. Typically, it's going to be the lodgepole pine in the Yellowstone ecosystem. It can be things like the Engelmann spruce or blue spruce, however. Now, in secondary succession begins on soil, pre-existing soil, or places where vegetation has existed previously. And so here, we start typically with, and fire would be a big factor here, and I'll come back to that in a second. So secondary succession, in a lot of cases in the Yellowstone ecosystem, is triggered by fire. And secondary succession is sometimes described as being a reversion to a previous state of succession. That's another way to describe it. So after a fire burns off the trees, if we're talking about a lodgepole pine forest or a spruce forest of some type, then again, there is existing soil. So rather than lichens being the initial type of organism that begins to grow, it's going to be plants, and it's going to be grasses, and like I said, fireweed, other annuals, sometimes some biannuals as well. And so these will constitute the pioneer species. And then, succession will progress more or less as we've described. Shrubs will then, begin to take over, that we've talked about before. And then this will transition into a mixed forest, and and those will be the equilibrium species, just as we described before. And then, if enough time passes, we'll eventually end up in this ecosystem, typically with a forest ecosystem of some type, lodgepole or spruce. So it's really the same basic type of succession. It's just starting at a different place. Instead of starting on bare rock, you're starting with soil and then progressing from there. Now, as we look at causes of succession, some causes of succession are allogenic, and so this would be from outside sources, and this would be the role of fire. By destroying the canopy, that's an external force that reverts us to a previous state of succession. And then autogenic changes would be those that are self-induced. So as grasses grow, die, contribute to soil, that then gives other plants an opportunity to get started. So in the Yellowstone ecosystem, again, one of the big changes in the ecosystem is caused by fire. It is a fire-related ecosystem, fire-dependent ecosystem to some degree. So, of course, in the Yellowstone Park and in the Yellowstone ecosystem, succession played a big role and got, more or less devastated the park in 1988. So that's when the major fires occurred. In the fires of '88, about 36% of the Yellowstone Park actually burned. As you can see, almost 800,000 acres. A big percentage of that was a crown fire, and a crown fire is a very hot fire. So that's a fire that gets up actually into the so-called crown, up into the upper canopy of the trees, as opposed to burning in the understory. The understory type fires are usually fairly cool. Once it gets them into the crown, those are really hot fires, and those are really hard to contain. Surprisingly, relatively few large animals died in the fire. Only about 300 large animals were confirmed dead. Most of those elk, you can see 246 elk, 9 bison, 4 mule deer, 2 moose. So generally animals just get out of the way, they move on. But occasionally, like our own firefighters, they can get trapped in some situations. But it is important to know that in this ecosystem, that is something you have to take into account, because fires occur every year in this ecosystem. So, when you're hiking in the ecosystem, you have to be conscious of the time of year you're there, what the fire danger is, and always be packing, for an extended hike, because again, a fire could come in behind you conceivably. You have to be aware of those kinds of things, and it can be dangerous. So continuing on with the fires of '88 then, what's kind of interesting about this is that we learned a lot about succession, some things that we didn't really realize about the ecosystem. I've kind of described what it is, the typical succession in the ecosystem, but we have seen some unexpected differences in this as a result of this fire. So generally, aspen has expanded its range. That was more or less anticipated, but not nearly as much as was thought would happen. It was thought that aspen actually would really expand greatly after the '88 fires, and it's only been kind of a modest expansion. And generally speaking, where aspens were growing previously, aspens have grown again, and where lodgepoles grew previously, lodgepoles have grown again. So we're not really seeing that transition from a mixed forest, to a climax forest. It's just basically whatever was growing there before, that's what's growing up this time. So it isn't hasn't read the book about how secondary succession should progress. Of the large animals, moose has probably suffered the most from the 1988 fires. There was a lot of willows habitat which they feed on that was lost. Some of the alpine fir stands were lost as well. And those are important food resources, especially in the winter. And then also with a decreased canopy, that allowed more snow to get to the ground. And also, it also decreases their forage. So again, the willow loss decreases their forage, and then also the canopy loss led to deeper snow, and they don't do well in deep snow. They don't really care for that. So anyway, so they have suffered probably the most as a result of those fires, or at least initially. Now, we've talked about, some examples of secondary succession here as a result of fire and what we've observed. But the thing about succession is there are lots of different types of succession, and especially in this ecosystem, there are a variety of different types of succession. So I'd like you to take a look at a video that we prepared up in the Yellowstone ecosystem last summer that discusses another variation of secondary succession. The reason I'm standing in this slough in Yellowstone National Park is to show you an example of secondary succession in action. What I'm standing in is a natural drainage which occurs during the late spring and early summer as the snow melts. And again, this area is known as a slough here in the Yellowstone National Park. And you can see an interface then between the slough and the coniferous forest behind me, dominated by lodgepole pines. The reason lodgepole pines aren't growing here is that it's just too wet. Basically, the water would drown the roots, and so the trees really can't get started in this area. Now, what happens over time, though, is as the water moves through here, you can see that grasses, sedges, other plants have grown in the slough, and they slow down the rate of water flow. And as a result of that, then, the sediments are taken out of the water, and the sediments begin to accumulate in this area. As the sediments accumulate, it raises this area, makes it drier, and then that allows the conifers to intrude into this area and grow into the slough. So what tends to happen in these kind of situations then is that we go from a wetland to a seasonal wetland, and eventually coniferous forest will grow in and make this ever smaller. So again, there are many, many examples of secondary succession in nature, literally thousands, and this is just one of those many thousands. Now, we also see transitions potentially in lake ecosystems. And when we look at lake ecosystems, one of the problems here, and previously, and actually in the first module, a supplement to that, I talk about the different types of lakes, the oligotrophic lakes, mesotrophic lakes, and eutrophic lakes. But one of the things I didn't tell you at that time is that we do have potential transitions, rapid transitions from oligotrophic or mesotrophic into a eutrophic condition. And being a eutrophic lake is not a bad thing, but it can be potentially a toxic situation. And so this is one of the things we have to be careful of in the Yellowstone ecosystem, because this is usually the result of pollution. So it begins with increased nutrients coming into a lake. And these increased nutrients then will lead to an algal bloom or aquatic plant bloom or both. And if that nutrient influx then is interfered with in some way or decreases, then algae and plants will die. That creates a resource for decomposers to feed on them. So as they feed, decomposers will bloom, and so this will be fungi and bacteria that are in the water. And as they decompose the material, they're heterotrophic, they're going to be sucking oxygen out of the water, so oxygen content of the water plummets. This in turn then will lead to a fish kill. Fish begin to die. This feeds back, helping the decomposers, so that's just more food for the decomposers, so they continue to decrease oxygen levels. And eventually, you'll have a lake that really cannot sustain any kind of aerobic life. And this leads to a quote-unquote dead lake. And then you'll have a bloom actually of anaerobic bacteria. And it's not truly a dead lake. Some things can live there, but only anaerobic bacteria can live there. So this scenario is unlikely in the Yellowstone ecosystem, but to get to this extreme, but pollution in lakes is always a concern, because you don't want to get to this kind of situation. Along the periphery of the park, it is a possibility, but in the parks, it's probably fairly unlikely. Now, there are, as I said, many different types of succession, getting back to terrestrial succession, but we do see some general trends. Generally speaking, early in succession, if we look at where nutrients are found, they're mostly in the soil early in succession. Late in succession, it will be tied up in the biomass. Early in succession, biomass will be low. Late in succession, it will be high. Diversity is usually low early, and usually higher at least late in succession. Although I have to say that in some mature ecosystems, climatic ecosystems like lodgepole pine ecosystems, there's not a lot of diversity, so I don't want to generalize too much there. And then generally speaking, early in succession, species are so-called R-selected, meaning they are short-lived and reproduce quickly. And then late in succession, we tend to see K-selected species, which means that they are longer-lived and reproduce more slowly. So again, in these aquatic ecosystems where eutrophication can occur, pollution is something that we have to be concerned about, and that can be from increased runoff. Also, pesticides potentially can lead to that problematic succession. Okay, now some other important dynamics that occur in ecosystems are feedback loops. And so when we look at feedback loops involve some kind of a stimulus that leads to a response that feeds back on the stimulus in some way. And there are two possible feedbacks. There's positive feedback and there's negative feedback. So when we look at feedback loops, again, one example would be positive feedback loops. And so what I'd like you to do is take a look at another video that we filmed last summer looking at a positive feedback loop. Positive feedback loops are fairly rare in nature. The reason is that they tend to take an individual physiology or an ecosystem away from the status quo. And again, that's fairly rare. So a positive feedback loop then would involve some kind of a stimulus that triggers a response that feeds back on the stimulus, increasing the stimulus, which would then increase the response, which would in turn increase the stimulus even more. So you can see how this situation then would spiral away from the status quo. So one of the places where we can see this is in population cycles, and I'm standing in Hayden Valley in Yellowstone National Park, and one of these population cycles involves the bison population. So bison effectively here would be the stimulus. And what they do is rub on trees, kill the trees, thereby expanding grassland. In other words, they deforest this ecosystem. That increases the amount of food. That essentially is the response. More food leads to more bison. More bison leads to more deforestation, which leads to more bison. Which more deforestation, more bison. So you can see that the bison population then would just continue and has continued to increase and increase and increase. So with positive feedback loops, then there has to be something coming in from the outside to break the loop. And typically in population cycles, what that would be disease, perhaps some kind of new predator would come in. But again, it's going to take some kind of outside force to get you back to the original situation. Now, the other kind of feedback loop then would be negative feedback. And in a negative feedback loop, instead of the response increasing the stimulus, the response is going to decrease the stimulus. And when we compare positive and negative feedback loops, as discussed, positive feedback takes you away from the status quo, and you need something coming in from the outside that will interrupt a positive feedback loop. A negative feedback loop helps maintain the status quo. And so most physiological systems, at least in warm-blooded animals then, are negative feedback loops. So if for example, if your blood pressure goes up, it will stretch receptors in your carotid arteries. That sends a message to the brain to decrease your heart rate. That lowers blood pressure, takes you back to original blood pressure. So physiological systems are generally negative feedback and help maintain the status quo, maintain this homeostasis of our physiology. But we also tend to see negative feedback systems at work in ecosystems as well. And an example would be if you look at beaver behavior in beaver ponds. Beavers will build a dam across a stream. They do that to back water up and form a pond. And a lot of times when I ask students, what do you think that pond is for? They think it's so that fish will be there and so that beavers can feed on the fish. But you may recall when we talked about beavers, they don't feed on fish, they feed on vegetation. So what that pond is about is that as the water backs up behind it, then they can build their lodge in the pond, they can have an opening to the lodge under the surface of the water. That helps protect them from carnivores, which may try to eat them. So it's basically, and I know I talked about this before, but basically to build a moat around that. So if the dam begins to leak then, that would be the stimulus. Water level is going to drop. That's going to be a problem from them, opening up making the opening of their lodge available to predators. So that triggers a change in their behavior. They will now go cut down trees, strip branches and so on, and they'll plug up that leak. That stops the leak, and then they go back to doing whatever they were doing before. So the stimulus would be the leak, the response would be to plug up the leak, and that stops the stimulus, which was the original leak. So that would be an example of a negative feedback loop from nature and from this ecosystem. Now, synergism also is something that is a concern in trying to manage ecosystems and anticipate problems. And synergism is where you have combined effects that are different than what's expected. And so there is positive and negative synergism. And in positive synergism, the combined effect, usually here we're talking about chemicals, the combined effect of chemicals is greater than what is anticipated, a 2 + 2 = 5 kind of situation. In a negative synergism, the combined effect is less than what you expected. The problem is that you don't always know what's going to happen in synergism, and we don't always know what kind of toxins are going to wash into the ecosystem. So the problem is you end up with animals typically starting to die, and then you have to figure out what's killing them. Is it a biological entity? Is it a chemical entity? If it's a chemical entity, is it a combination of chemicals? What's the combination that's going on here? And then can we eliminate these chemicals from the ecosystem? So there's a lot of development going on in and around the Yellowstone ecosystem that potentially can be problematic for species in the ecosystem, so it's something that's constantly being monitored. Another dynamic that has to be considered is biological magnification, again typically involving toxins, and this involves primarily fat-soluble toxins and metals, so-called heavy metals like mercury, lead, things like that. And so what happens with these, and one of the places where it has affected the ecosystem involved DDT, going back in the 1960s. As we've talked about, a lot of fish-eating populations crashed back in the 1960s, and bald eagle was one of these. And eventually what was determined is that it was DDT, a pesticide, that was causing this problem. And what was happening is that DDT levels were concentrating in the bloodstream of these fish-eating birds. So this was also including the pelicans in the ecosystem as well. And it would reach toxic levels in their bloodstream, affect their reproductive anatomy and physiology such that they were producing eggs that had shells that were very thin. And so when the hens would sit on the eggs, they would break the eggs. And so this is why the populations were crashing. So it wasn't really a behavioral problem, it was a physiological problem. So when you looked at their tissues, you had very high levels of DDT, yet when you looked in the ecosystem itself, DDT levels were very low. And so what was happening was that DDT being fat soluble, each step in the food chain acted like a sieve in effect. So as DDT was taken in by zooplankton, microscopic organisms in the environment, as they would drink the water, for example, they would take in DDT. And every molecule of DDT that they take in would get trapped in their fatty tissues. It wouldn't be flushed out as water-soluble materials are. And then whatever fed on them would not only be consuming that tiny animal, but all of the DDT in their tissues. And all of that DDT would stay in their tissues. So this might be the primary consumer. And then that DDT would go to the secondary consumer, and the amount of DDT in their tissues would be greater still. And then as you keep going up the food chain, every step in the food chain, the toxin would get magnified more and more and more because it never gets flushed out of the system. And eventually reaches toxic levels as you get up into the higher levels of the food chain. So this is biological magnification. And again, part of the problem here is that you start seeing animals dying or they're not reproducing normally, and then you figure out, there's this chemical in the environment, and then, can we fix that? Can we get it out of the environment? And then hopefully you can. So in this case, DDT use in the United States was stopped, and all of these fish-eating birds that were picking up DDT that was washing into the aquatic ecosystems have recovered. So the bald eagle have recovered, the brown pelican along the Pacific coast, white pelican in this ecosystem, osprey, have all recovered nicely as a result of that. Now, another dynamic that's constantly being evaluated is the predator-prey relationships. And so for a long time, biologists have tried to seek out and find a formula that we can apply to all predator-prey relationships. And bottom line is that we really don't have that universal equation that we can use. One of the longest studied relationships is the lynx snowshoe hare relationship. And so that one is one that we do see observed again for centuries, quite honestly. And what is true of natural populations, I think we have this idea that in ecosystems that populations are stable, that they maintain themselves from year to year. But as you can see here, obviously what we really see over time are dramatic fluctuations in populations. And so this is the norm. This is typically what we see. And so in trying to understand these dynamics, what we eventually figured out is that there are three primary forces at work in causing these cycles. And we're learning a lot about these and being better able to predict changes in populations. The problem is, though, that we have to study each of these interactions. So there is no universal formula. We have to get out in the field and try to understand all of these individual dynamics, and then we're able to actually predict what's going on. So anyway, some of the factors that play a role, one would be the prey animal and its food availability. So if there's a lot of food, generally population goes up, but that's not always the case, but that's one of the factors that we consider. Prey density also is a factor potentially in cycling, because in some situations there may be plenty of food to support more prey, but if the prey density gets too high, They may become aggressive with one another. They may actually stop reproducing. It really depends on the behavior of the specific animal. So again, unfortunately, we can't make broad generalizations about this, but prey density definitely plays a role in cycling. And then the third factor that plays a role in cycling is predator density. So as predator numbers increase, obviously they're going to be eating the prey, and at some point that's going to impact the population as well. And then if the prey population decreases too much, then the predators start starving out and they'll follow that population. So again, universal formula, no, but these are the three major factors that play a role in the cycling of different types of animals. So when we look at ecosystems, then there are a number of dynamics that we have to consider. And so we constantly monitor ecosystems. We a lot of times do the same work over and over and over again. And so there are many ways to evaluate and monitor what's going on in ecosystems, and one of these is what's known as a quadrat sample. It comes from the name originally in using some kind of a quadrangle or rectangle to evaluate species within. But basically what you do is you lay out a grid of some type. It might be a small grid, it might be a large grid, and then you'll look at all of the plants within that particular grid, and this is normally when you're looking at plant species. It doesn't have to be a rectangle, it could be a circle. So in looking at forest ecosystems, you might pick a tree, go out a certain radius, and then identify all the trees within that particular radius. And then this is typically combined with what's known as a transect. So you'll run a line, it might be for 1,000 yards, 2,000 yards, 5,000 yards. You might run these in different directions, and then you'll lay out your quadrats and do your quadrat sampling along these transects. And so what you do then is you'll build vegetation maps from this. You could also do this for sampling animals as well, but typically these are vegetation maps that are built this way. We look at the animals. So one way to estimate animal populations is to capture, tag them, and then release them. And then go back, recapture, see how many of the recaptured animals you've tagged and identified before, and then you can make population estimates from that. A kind of revolutionary way, though, is to actually use DNA fingerprints. So what we have begun to do, rather than capture animals, is actually create what we call fur traps or hair traps. Put out roadkill with either tape or barbed wire around it, and as animals come in, they'll leave behind hairs. Those can be pulled off and fingerprints established, and we can find out where they are. And then also in the park, they do aerial surveys, usually once a year, for some of the large mammals in the park. So these are constant surveys that allow us then to look for changes in populations, and if we see dramatic changes, we try to figure out what's the cause of the change. Okay, that'll do it for today. See you next time.